We are very happy to have confirmed this resonance, this particle, which in fact is a very strange object. This object was already discovered in about 10 years ago by Bell experiment at the Japanese E+- machine with lower statistics. And the strange thing is that it does not fit very well into the quark model invented by Gell-Mann and Zweig just 50 years ago, was 64. It's quite amusing that the quark model, which is very simple in principle and foresee for our world, a world made of either two quarks or three quarks, which are joined together by the strong force. As I said, it's quite amazing that a few years after the invention of this very simple and very nice model, particle physicists already discovered some anomalies in this model. And in fact, this particle is a striking anomaly because it's evident that cannot, for several basic reasons, it's evident that cannot be made of only two quarks, as we expected from the Gell-Mann and Zweig model, but it should be made of four quarks.
We have now undisputable proof that nature is actually able to form more complex, more sophisticated objects of quarks than were initially proposed by Gell-Mann in 1964. Up to now, we have only seen objects of three quarks or a quark and an anti-quark. In this particular case, LHCb has analyzed 250 billion events where, in fact, the LHC has produced a BB bar. And in these cases, we have 25,000 interesting decays of a neutral B meson. In this particular case, the B meson decays to three particles, and by analyzing the outcome here, we can see if nature has a tendency to form objects in the intermediate stage in the decay process. And what we have seen is that nature is actually forming an object of four quarks, what we would call a tetraquark. This was not part of the initial proposal of the quark model, but we've suspected all along that the strong interaction should in principle be able to do this. But it's the first time we have really undisputable proof that nature can form an object of four quarks together. For 40 years, we had actually no evidence of this kind of more exotic objects. There were the first hints coming about 10 years ago from the Babar and the Bell experiment. We started to call this object professionally by the name Z, and in fact it's a negatively charged particles with a Z minus. So the particles we are studying, they are nowhere naturally existing in today's universe. All of these objects are basically part of a very early history of the universe, approximately a microsecond after the Big Bang. However, this particular long-range behavior, the dynamics of the strong force, is something that takes place in all kinds of places in the universe, in particular, for instance, in the formation of nuclei, etc. But we could even have implications of this understanding in the understanding of the compositeness of a neutron star.
It is also amusing to see that we know that our universe is made of mostly of dark energy, is made mostly of dark matter, and only 4% of real matter, of everyday matter, is known to us. But this kind of searches demonstrate that even this 4% hides secrets, and we need a better understanding also of the matter which is under our feet.